Hello everybody and welcome. We are in lovely Milan at the lovely Mafra place and we're with the lovely Reggie Cox. Today we are going to go and have a little whistle-stop tour through the factory, through the storage and through all the facilities they've got here, and ending up in the chemistry lab where there are going to be chemists and we're going to talk about chemistry. So that should be fun. Come and join us. Hello and welcome to the secret labs behind Mafra, where we make the Laboco스메티카 range.
Yeah.
You develop the range as well.
Yeah, a sort of cosmetics for your cars.
Exactly. And these two chaps here are the chemists, the brains behind the range. Why don't you just introduce yourselves to our watchers?
Okay, you start. Everybody, hi everybody. I'm Riccardo. I'm the R&D developer of Laboco스메티카, and he is Giacomo. And
hi everybody.
We are the Laboco스메티카 team, and we develop a lot of products, whole the line from detergents to coatings, sealants, and so on.
And what I wanted to do is talk about pH, because pH is a topic that regularly comes up in detailing, and my knowledge of it is like this compared to you guys.
Yeah.
So I tell you what, who invented pH and when did it sort of become a thing?
Okay, we want to start you.
Okay, just for clear things, we know that we have a water solution, and basically water molecules can be in room temperature can be split in two things: protons and other atoms, ions called. And those two things balanced together, they give us the value of pH. If there are more protons, we can say the solution is acid, and therefore pH goes down. If we have more OH minus, this is the counterpart of the water. If that counterpart prevails, you will have higher pH alkalinity. Both having too many of the two species, so if you have an alkaline pH or acid pH, is dangerous for a delicate solution, because those ions can interact with regular matter and they act, and what we see is the sparkling on the surface means those those ions are going to degrade our surfaces, and the damage could be permanent, of course. That's why we want ideally that those two species are balancing one to each other, are present in the solution in the same concentration. So you have a neutral pH 7.
Of course, yes. Actually, chemists all over the world use pH as a standard measure parameter to evaluate solutions, liquid solutions, alkaline solutions or acid solutions, to of course understand the characteristics of the products and of course the causticity also of the products on metal panels and metal surfaces. So this is now after 110 years history of pH, pH became a standard measure for the laboratories all over the world.
And so pH was invented, you were saying 1909, was it?
Yes, from Carlsberg beer.
That's brilliant, from a brewery, basically.
Inside the Carlsberg beer laboratories.
And
so,
the H stands for hydrogen.
Yes, H stands for now in easy words stands for concentration of hydrogen ions, and P. There is a little cool history about P because you can find on websites that the P stands for power of hydrogen. That is cool if you heard these words, but this is not the real meanings. But P was only the name of the solution identified with the P letters because 100 years ago P and Q was standard letters using algebra and maths.
It was a symbol.
So symbols, by symbols.
Actually,
Exactly.
P stays for the minus logarithmic function.
Yes,
That's
exactly.
why you have a range between 0 and 14. Because you have a concentration which is a very, very, very low number. And so you apply the minus logarithm function and you have a natural number between 1 and 14.
But from a detailing point of view, and as you alluded to earlier, is that if you have something that's too acidic or too alkaline, it can potentially damage a surface irreparably in certain cases.
Exactly.
But what I wanted to cover slightly is because Labo create quite a few acidic products and quite a few alkaline products,
Yes, indeed.
but presented as safe to use. And we've seen demonstrations where on aluminium plate, you put something with a pH 2 next to something else with pH 2. So we used, what was it, the sort of acid, sulfuric acid, wasn't it? That you were
Yes,
using?
sulfuric
Or
acid
hydrochloric.
or hydrochloric acid.
Inorganic acids, yes.
It's a very powerful acid.
And that had a similar pH to the product, but of course that was fizzing away on the aluminium and the product wasn't. And so despite being a similar pH, what is the difference between those two ones, the ones that damaged, i.e. the acid, and the product? Why does the product not damage the metal?
Actually, it's the what I said earlier, because the number is just value. It comes from a mathematical interpretation. The minus logarithm function just makes everything flat. If I have a very high concentration of protons or just a small amount of protons, the minus log function just flats out the upcoming number. Okay. So both of those solutions will have a natural number as results, pH 0 or 1. But that number really does not mean the real concentration of the protons inside the solution. That's the real deal. So even if we know the exact number of pH, we are not aware of the real concentration of protons inside that solution.
When using just pH as the measure.
Yes, exactly.
So this is in short, essentially, pH 2 isn't necessarily going to be dangerous because it could be pH 2 but at a very low concentration. Equally, pH 4 could be more dangerous than pH 2 if the pH 4 is at high concentration. And the same happens in reverse. We were trying with NaOH, wasn't it? Sodium hydroxide.
Sodium hydroxide, yes.
Was one of the example. Now,
Potassium hydroxide, yes.
Yeah, it's not nice stuff. You don't want to drink that.
Exactly.
No, absolutely not.
For very high concentrated products, it's very difficult to evaluate the real causticity on without practical devices or tests. Of course.
It's not just a matter of pH because there is a set of raw materials you can use in your products that even if they are neutral pH, they can be dangerous. Mm-hmm. It's just because they are different chemical raw materials with different natures, and the natures of the raw materials can cause damage or can prevent damage. Simply as that.
So in short, when you see a product saying it's pH neutral, it doesn't necessarily mean it's safe. And when you see a product that says it's quite alkaline or quite acid, they don't necessarily are dangerous. And the other element is, in order to achieve a change, so achieve cleaning power, there are various different ways you can do that. So you can do that from the sort of chemical side. Explain the different systems that...
With surfactants, type of surfactants, other chelating agents, and so on. So we use, of course, the pH, so the alkalinity, bases and acids to increase and balance the detergency, the cleaning power, the general cleaning powers of our products.
So again, when you're talking about the neutral products, don't presume they're safe, and the alkaline ones and acid ones, don't presume they're dangerous. And in terms of what they actually do, in terms of how strong their cleaning power is, generally speaking, you may have to be slightly acidic or slightly alkaline to achieve that, but it doesn't mean that they're going to do damage to your paintwork. That's more down to what these guys do, and that's why they test it, and that's why it's safe. So that's an interesting little insight into pH. If you're going on a first date, for example, you could bring that topic up. I imagine that would work very well. Or if you have friends and family over and you want them to leave quite quickly, you can also describe the situation. Anyhow,
don't worry about pH. that's the fun.
There are other things to worry about, much bigger things. Anyway, thank you very much, guys.
You're
It's
welcome.
been appreciated. Thank you for letting us in. We're joined here by the beautiful Reggie No, we probably ought not call him the beautiful.
You're saying he's not beautiful? That's not very nice.